Thanks for asking me to speak here and organizing this nice conference. All right, so I'm going to give myself G over QP, some connected reductive group, which I'm going to assume is split because life is short. And I'm going to be interested in, well, discussing the local Langlands correspondence. So what does that involve? So on one side of the Langlands correspondence, you consider, or local Langlands correspondence, you consider the following set of smooth, irreducible representations of the QP points of this G on K vector spaces. Where K for me in this talk is either going to basically be QL bar, so the algebraic closure of the complex numbers, so L is a prime distinct from P, or it's going to be given by the complex numbers. And I'm just sort of freely going to pass between these two things in this talk via some fixed choice of isomorphism between QL bar and C, so I'm not going to really worry too much about what I'm doing here. So I'm usually going to regard this as having the discrete topology. And let me maybe mention like one tiny technical point, which is, so I want to talk about the Fargues-Scholze local Langlands correspondence, and that essentially comes from this Hecke action and this excursion action, and that's determined by some choice of a square root of P. And if you really want to compare Fargues-Scholze with some kind of local Langlands correspondence over C coefficients, it's important that you fix that choice of square root of P to correspond to, so this is some map I, to the pre-image of this. But I'm not going to worry about this too much, right? So on the other side of the correspondence, I'm going to consider, well, parameters. So there's been multiple different conventions for how to think about parameters and some discussion about how to pass between them, but I'm going to think of parameters as just being given by some homomorphism from the Weil group of QP times SL2 over, let's say, QL bar towards the Langlands dual group, GL-QL bar, which I'm going to assume are Frobenius semisimple. So in particular, if I look at the image of Frobenius, that should define a semisimple element inside this dual group over here. So this SL2 is essentially encoding the monodromy. And I'm going to consider these up to, well, G hat conjugacy, and maybe I should also say up here I'm considering this up to isomorphism. Right, so the local Langlands correspondence links this set pi G with this set phi G, but we also want to consider what's known as the Fargues-Scholze correspondence, and that relates this set pi G to a slightly different set, which I'll call phi SS of G. So this is going to be basically the set of maps from the Weil group of QP towards G hat of QL bar, so there's no SL2 appearing here, and moreover, we're going to assume that these maps are semisimple. So in other words, if it factors through some p hat where p is a parabolic, then it automatically factors through m hat. So what's the goal of the talk? So for some LLCG, as in Alex's talk, so that satisfies this various properties that Alexander wrote down. So we got some map going from pi G to the set phi G, which I'll call LLCG. And let me, maybe as shorthand, I'm always just going to write, when I write phi pi of a representation, what I really mean is this local Langlands correspondence over here. Well, we want to compare this to the Fargues-Scholze correspondence, so we have some LLCG Fargues-Scholze that's going to map this to the set of semisimple parameters. And then, well, we need to somehow compare these two things. So I zoomed in. So in particular, there's a map from the set phi G to the set phi S of G basically, that's done by killing this SL2 factor in a way that gets rid of the unipotent part. So there's some map over here. And this is given by sending some element in the Vig group of QP and then mapping it to this determinant 1 matrix where this absolute value sign denotes the norm character. So you just precompose with the natural map sending W of QP to G and then this determinant 1 matrix. So in particular, we have this map over here, so SS. Well, we want to show that this diagram commutes. Show that this diagram commutes. All right, so maybe I should say briefly something about why we would want to do this. So I guess in the context of this, this conference, it's because, well, Hansen and Mann use this. So that's maybe one reason to care about doing this. In particular, I think various results in this paper rely on knowing certain properties of these Fargues-Scholze local Langlands correspondence. So there's maybe just a basic question that we don't know how to answer that let me just highlight, which is, if you take some semisimple L parameter, then, well, you can look at just the L packet or the fiber of this Fargues-Scholze correspondence, and we don't know in general that this is finite. So even if you could just show this finiteness in general, that would already be extremely powerful. But let me maybe present a slightly deeper motivation that will get into maybe addressing what the Fargues-Scholze correspondence really is. So what the Fargues-Scholze correspondence really comes from is, well, we consider this, I think this was called the spectral Bernstein center, which is the ring of global functions on this moduli stack of L parameters, which also just identifies with spec of this as the affine scheme defining the coarse moduli space. So in particular, a maximal ideal inside here is the same as some closed point inside the coarse moduli space, and that corresponds to a semisimple L parameter. So a maximal ideal inside here corresponds to a semisimple L parameter. So I think this was discussed in Zhen Chen's talk. I'm sorry if I mispronounced. Yeah, right. So in particular, this ring of global functions, it can also be thought of in terms of what are known as excursion operators, and those act on the derived category of sheaves on this moduli stack of G bundles. So this Lease et al., if you want, or D-rel, or whatever's in vogue these days. Right? And in particular, if you have some ring acting on some category like this, well, then just like with a usual ring acting on a module, you can take the localization. So in particular, for phi and phi SS of G, you can form some kind of localization with respect to some maximal ideal defined by the semisimple parameter. And one of the reasons that compatibility is extremely useful, I mean, not just in this work of Hansen and Mann, but just in general, sorry, so we call this localization D bun G of phi, is that it allows you to describe this. It allows you to describe this localization. So what this localization is effectively doing is, I mean, this category is built out of smooth representations of these various GBs and so on, and it's basically fixing the Fargues-Scholze parameter of the representations appearing in there to be equal to phi. And so if you have some good control over the Fargues-Scholze correspondence, then you know exactly which representations can appear. So at a very basic level, this is why you would want to understand this. Okay, are there any questions on the basic motivation for what we're doing here?
So why is it useful to consider this localization?
Sorry?
Why is it useful to localize it?
Well, I mean, I think this may be talked about next week, but you can kind of break up the categorical conjecture if you want in terms of these different localizations around semisimple parameters. I think for this, it's strictly better to work with sort of a formal completion around this, but you can sort of take life one parameter at a time if you want to prove this categorical conjecture, right? Yeah, I mean, also, if you want to study cohomology of Chamorro varieties or things like this, you also pass these kind of localizations around a fixed parameter and then study the behavior at each one. Right. Okay, cool. So what is known? I worked on this a while ago, and I feel like I'm a bit out of the loop, to be honest. But let me try and report on what I think is known. So first, let me just write the Dinkin diagram of various groups. So let me consider groups of type AN. So here, the relevant local Langlands correspondence is unambiguous, so it's the one given by Harris-Taylor, so like GLN. And this was essentially already done by Fargues and Scholze in their original paper, and I guess I'll sort of explain why later on in this talk. And so where I came in is, I guess, is for groups of type C2, so something like SP4. So that was the next case that came after this. And then also, so I should say I think this was discussed in Alexander's talk, but so once you have like Harris-Taylor, there's some way of getting some nice local Langlands correspondence with all these various properties, using that various classical groups can be written as sort of fixed points of a given involution acting on that classical group. So this is the phenomenon known as twisted endoscopy. So when I say compatibility in all these cases, I mean these kinds of local Langlands correspondences coming from Harris-Taylor and this twisted endoscopy. I'm not going to write all the names of all the people who contributed here, but this came up in Alexander's talk. So you could consider, for example, unitary groups, and this was done by myself together with Alexander. Sorry. I need to package knowledge. And then, well, basically the method in here was cleaned up a lot in work of Hamann. So I think, right, so for groups of type Bn, so Dn, where there's a little bit of an asterisk here about what you mean with local Langlands. And then just also for general unitary groups, this was basically done by Peng. And then, well, these various results up here, they had various restrictions related to basically integral models of Chamorro varieties. So there were various restrictions, which were recently removed in work. So were removed in work of Van Hoften, Kim, Daniels, sorry, I'm not doing the order correctly, and Jean. Yeah, sorry, yeah, this is one group of authors who did this. As we'll see in some point, you kind of need to make Bunji, which is in some sense defined over FP bar, you need to somehow make it talk with the rigid generic fiber of the Chamorro variety. And the best way to do this is using integral models of Chamorro varieties. So this is really where their work came in, was in getting the most general results necessary for establishing this. So I just wrote the Dinkin diagram of this, but let me just say some points here, which is you could, for example, consider central isogenies of groups. So you can handle central isogenies, at least assuming you know there's a good local Langlands correspondence, which, as Alexander mentioned, can be quite technical, central isogenies. Essentially because you know that Fargues-Scholze has some expected compatibility with central isogenies.
So just for the record, can I ask you to write the word some central isogenies or something?
Oh, yeah, sure. Yeah, I mean, if people really want to know about this, we can talk about it later, but it's just very technical. And also, you can handle also inner forms. So I assume my group was split at the beginning. And this essentially uses some work of Hansen, Kalitha, and Weinstein. And so I guess this will come up in a little bit. Right. So that's the state of affairs, but let me just emphasize, it's like, what do we not know? What do we not know? Well, finally, we, at least in this setting of classical groups where we roughly know what the local Langlands correspondence is, we don't know symplectic groups for higher than SP4. So there's a big question mark here. So there's some fundamental obstruction with this method here. And then, well, we don't know anything for exceptional groups. So here, basically, there's some very general construction due to Kalitha, and you could ask if it's compatible. And for G2, there's some definitive work of Aubert and Zhu and Gan and Savin. But maybe I've actually been informed that there's some work of Kottner and Tony Feng. So Sean is here. And also some work of Chenji Fu that actually gets at this question over here rather remarkably. I should emphasize, it seems that like to address these cases, you need to somehow prove some kind of functorality of Fargues-Scholze, and Tony in some early paper was able to do this using some ideas around Smith-Truman localization. But yeah, so that's at least the state of affairs as I currently see it. But I just want to address roughly this thread of ideas up here. So let me say, like, what's the key idea? So what's the key idea? Right, so this Fargues-Scholze local Langlands correspondence, it's built from these excursion operators, which in turn come from these Hecke operators. So in particular, if you fix some dominant co-character of your local group, so some maximal torus sitting inside there, well, as we've seen, that determines some highest weight representation of G hat, and also some homomorphism R mu from G hat to GLV mu. And, well, geometric Satake will define some kind of kernel sheaves attached to these highest weight representations, and that will in turn, via pulling and pushing along some space of modifications, give you some operator taking sheaves on this bun G to sheaves on bun G equipped with some continuous action of the Weil group of the reflex field of this co-character. So this is, so E mu is the reflex field. And in some sense, this Weil group action is encoding the fact that you can move your point around in this weird kind of mirror curve or Fargues-Fontaine curve. Right, so somehow we need to connect this more classical versions of the local Langlands correspondence with this kind of operator over here. And to do this, let's maybe just first peel away some of the structure on this. So in particular, this category of sheaves on bun G, it has some kind of semi-orthogonal decomposition on it. So in particular, you can take your operator and maybe restrict it to the locus defined by the trivial G bundle. And so in particular, that will mean that the target of this operator will now just be sheaves on the neutral strata, which is just smooth G of QP representations, together with some Weil group action. And then maybe for some suitable B, so in the set BG mu that Mingja mentioned, so that we guarantee that this operator is not trivial, we can...
Tiny comment?
Yeah, sure.
Their base field could be QP, right? And your group was split, so this E mu thing can just be QP, actually.
Oh, yeah. I guess that's, yeah, sorry. Yeah, thank you. Right. All right, so this will be QP. Well, okay. Let me still write E mu, because just to preempt what's going to happen later. There's too much notation to keep it all totally optimal. Right, so in particular, then this will take some smooth representation of this inner form, so the sheaves of strata on this B, to something over here, and you get some functor like this. Right, so now this is just a functor between categories of smooth representation, so okay, maybe it's a little bit more friendly than this full thing up here. But what is this really doing? Well, this Hecke operator was defined in terms of modifications of certain G bundles, and when you do these restrictions, you're basically fixing the isomorphism classes of the G bundles you're looking at. So in particular, what this is really computing is the space of modifications between the bundle corresponding to this B, this EB, towards the trivial G bundle E0 of meromorphy less than mu. So these are two G bundles identified outside of some point of the curve, and then it determines some lattice whose relative position is bounded by mu. And this is really computing the cohomology of this space. So we have the following funny shorthand for this, which is that we write this as taking R gamma C GB mu of some triple. So this is the cohomology of this kind of space. And, well, this GB of QP is essentially coming through the action of automorphisms on these two groups. And so, well, GB of QP will act on this cohomology, and you can take the tensor product over the smooth Hecke algebra, or take some RHOM, external RHOM in the category of smooth representations if you would prefer.
I'm sorry, but to be consistent, you might want to write PB.
Oh, sorry. Oh, man. Thanks. Yeah, so GB. And then there will be some kind of identification between these two things. So if this functor depends on something like this, it will be given by this isotypic component, and let's even give this some shorthand, R gamma C GB mu, and then we take the isotypic component of this over here. So now, okay, well, we just sort of repackage things, so it's computed in terms of the space of modifications, but we still need to somehow make this more concrete and more classical. So to do this, there's the following observation, which I still can't get over, which is due to Scholze and Jared, which states that if mu is minuscule, that such spaces of modification, okay, this is getting really dense. Such spaces of modifications are actually connected to p-divisible groups. So more precisely, the kind of space you're going to see here is sort of deformations of a p-divisible group xb over fp bar. So essentially, this is characterized by the fact that its crystalline cohomology gives rise to an isocrystal that corresponds to this element B. Deformations of a p-divisible group to O of Cp. So here Cp is the completed residue field of the p-adic numbers. So more precisely, you can look at some formal scheme defined by this deformations, and the space you're seeing here is really the rigid generic fiber, and then you're taking cohomology of that.
So could you repeat once again how did we get from the Hecke operator to the space of modifications?
In some sense, this just follows from the definition of the Hecke operator. So remember, the Hecke operator was defined by this correspondence where you had some modification of G bundles, and then you're sending it to E2 and E1. And then when you do this restriction, you're just saying that E1 is isomorphic to the trivial G bundle, and E2 is isomorphic to EB. So essentially, it's just proper base change on the definition of Hecke operators at the end of the day. Yeah, thanks for the question. Yeah, I want to emphasize here that really, okay, well, at the very least, you need to assume that mu is minuscule. But that's really the key restriction here. In general, yeah, I don't know how to interpret this in terms of classical algebra. Yeah, let's not get into all of that. If people want to know, then they can ask in the Q&A. I'm sure Jerry could give a very good explanation of all this stuff. Right, so great. What am I doing? Right, so in particular, this moduli space of p-divisible groups, this is something fairly concrete and classical. And so it's actually a theorem. Okay, actually, before I do this, let's maybe peel this away in a particular case. So let's maybe just do an example of this. So let's take the case where G is equal to GLN. And this mu over here will just be well, the co-character given by 1 followed by a bunch of zeros in the standard basis, or what corresponds to the standard representation. So R mu is just the standard representation of the dual group of GLN, which is, of course, just GLN. And so this B in this case, I'm going to take it to be sort of the isoclinic guy of slope 1 over n. So this cohomology over here, it identifies with the cohomology of some, of some explicit space, so which I'll call LTM, LTM, and then I'll take coefficients in QL bar together with some shift and Tate twist. So this is essentially just the dimension of this space, which in this case will be equal to n minus 1. And then you take the colimit of these spaces indexed by m as m is greater than 1. And really what this space over here is, it's the deformation space of a p-divisible group of dimension 1 and height n. So in particular, if the dimension, if we took n to be equal to 2, then that would be precisely the deformation space of a p-divisible group attached to a supersingular elliptic curve. And the action of GB in this case will be precisely through GL1 of a division algebra of invariant 1 over n. So if n was 2, that would be a quaternion division algebra, and that's precisely what you see in the endomorphism algebra of a supersingular elliptic curve. And this m over here, it's really just fixing some level structure on this deformation, and so that's what gives rise to sort of the GLN of QP action. So this is the Lubin-Tate tower. So this is the Lubin-Tate tower. Oh, and then over here, we also take the isotypic component with respect to the action of this division algebra. Right. So this space over here was studied for a very long time, and so it's a theorem that was actually proven by Harris and Taylor when they were trying to construct the original local Langlands correspondence for GLN, that if you take pi to be some supercuspidal representation. So a supercuspidal representation is in particular a discrete series, and there's some straightforward way of uniformizing discrete series representations in terms of representations of this division algebra. So we can consider what's known as the inverse Jacquet-Langlands transfer of this representation pi. So this will be some representation of this division algebra. And what they showed is if you take the R gamma C GB mu in this case, and you take the isotypic component with respect to this representation rho, so again, that's a GLN of QP representation with an action of the Weil group of QP, then the GLN action is given by the supercuspidal representation pi, and the Weil group action is given by the Harris-Taylor parameter of pi, where I should emphasize by the fact that this representation is supercuspidal, this SL2 doesn't appear. So like, there's no funny SL2 factor appearing here. Right, so we've done it. By God, we've done it. You know, we've connected the Hecke action to the classical local Langlands correspondence. So let me just emphasize precisely what's happening here. So we have this classical local Langlands correspondence, but on the other hand, this is really just T mu applied to some sheaf rho. So now let's go back to what the Fargues-Scholze parameter really is. So the Fargues-Scholze parameter is defined via, for example, for this representation rho, by looking at the action of this ring of global functions on this moduli stack of parameters. Right? So in particular, it's not too hard to believe that this kind of thing, so in particular this ZG hat acts on this row, and then that factors through the quotient of the maximal ideal corresponding to the Fargues-Scholze parameter of rho. But now we're applying this T mu to it, and so we need to think about what this T mu is. But the point is that this T mu, I'm not sure if this was discussed, but it corresponds also to some operation coming from this spectral action. So in particular, it corresponds to the tensor action by a certain vector bundle, which we call C mu. So this is a vector bundle on this moduli stack par G. And the way it's defined is by looking at the natural map to the classifying stack of BG hat, because we quotient out by G hat conjugacy. That defines, the highest weight representation defines a vector bundle on this BG hat, and then we pull it back. And the tensor action of this vector bundle corresponds to that. So roughly what's happening here is that you can kind of think, and this is actually how the proof of this goes, is you can think that this JB Schriek row is supported on some locus of the stack of Langlands parameters determined by this semisimple Fargues-Scholze parameter. And then we tensor via some vector bundle. But if we tensor, then by projection formula, we really haven't changed the support of the sheaf. So in particular, this thing over here actually should have, so we're seeing this representation pi acting on this CG hat. But because we see this representation pi inside here, we should also see that the Fargues-Scholze parameter of pi is the same as the Fargues-Scholze parameter of rho. Now, on the other hand, this C mu over here, well, it's actually not just a vector bundle on BG hat. So if you look at some point in this moduli space corresponding to some parameter, it more or less corresponds to the vector space V mu. But then that has a natural action on it. So in particular, that's given by, so this is sort of has a natural action by the Weil group of the reflex field. And that's given by sort of taking the universal Galois representation on the stack and then composing with R mu. So in particular, the fact that we see the Weil group here, phi pi, actually tells us that we should see in the Weil group action of this, well, R mu composed with phi rho Fargues-Scholze, but it's the standard representation, so that's the same. But the actual Weil group action we're seeing inside here is precisely phi pi. So in particular, it follows actually, I rushed through it because it would take quite a while to explain this all carefully, but it really follows formally from the construction of the Fargues-Scholze correspondence that if you have this isomorphism over here, that you get that this phi rho Fargues-Scholze is the same as phi pi. So in particular, this is why Fargues and Scholze were able to basically very quickly verify that their correspondence is the same as Harris-Taylor, because they already knew that the Lubin-Tate tower saw the Harris-Taylor parameter. Right, so that's how things work for AN. How much time do I have? I also started a little late, I guess.
Like 26 minutes or something like that. 27 minutes.
Okay, we're in good shape. Okay. Any questions on this? Oh, sorry, the C mu is just, oh, sorry, I should have had a check here. But there's a natural map from par G to the classifying stack of G check, right? Because you quotient it out by G check. And the category of coherent sheaves on this just identifies with representations of G check. So in particular, mu defines a representation, and then you can just pull it back.
Sorry,
right? So,
does it need to be a vector bundle on the parameter stack then?
oh, sorry, yeah, I just blew through this, my bad. Yeah, so this is, of course, on the parameter stack, right? Yeah, and then it's essentially constant, but you can pre-compose it with parameters, and that gives you this Weil group action on it. So are there any other questions about this?
How did you get like B rho Fargues and B pi Fargues all are the same?
Oh, Yeah, so you do need some kind of argument for that, but maybe the most succinct way is that the excursion algebra and the Hecke action commute with one another. So in particular, the excursion action will act on this row via this Fargues-Scholze parameter, and then you're applying some Hecke operator to it, and then seeing this representation pi via this result of Harrison-Taylor. So in particular, the excursion algebra will act on this pi, which is seen inside this Hecke operator via the same way that it acts on rho. So that's why these two are actually the same as one another. If you want like the tensor action of this vector bundle C mu, it doesn't really change which locus on the stack of parameters you're supported on, essentially by projection formula.
Is that just because you're picking mu corresponding to the standard or?
No, this, sorry, I should emphasize, this works for any mu. The Hecke action and the excursion action commute with one another, right? So anytime you compute like these kind of local Chamorro varieties or spaces of modifications and you see representations, then it will tell you it's the same as the representation that you originally started with. So this is a very useful idea. So does that make sense to everyone, kind of? Okay, anyway. All right, great. So on the other hand, like, Alexander in his talk, he wrote down this local Langlands correspondence that had this very long list of properties and so on that were characterized by these complicated trace identities with these centralizers and things like that. And you might have a question just at a basic level, like, why does this deformation space of p-divisible groups have anything to do with what was written down in Alexander's talk? And so let me explain this in the following way. So the properties Alexander mentioned, really come from studying, global Langlands. So they come from studying the discrete spectrum of the following group. So we consider maybe some group G over Q, such that if I base change G to QP, I get this group G. And then I consider this kind of adelic quotient over here. So this is some space equipped with some kind of measure on it. You can make sense of some L2 space, and then you can consider sort of the discrete portion of that. And, well, that's kind of built from some representations pi. So G of A acts on this. And this is built from some restricted tensor product of representations pi v, which are like the ones you saw before. Essentially, basically, there's a very powerful tool for studying this known as the trace formula. In particular, that's exactly the tool that allows you to propagate local Langlands from GLN to other groups. And a lot of these things that Alexander was writing down was motivated essentially by, studying this thing through the lens of this trace formula. So we need to somehow connect this question over here to this deformation space of p-divisible groups over here. So the way we can do this is by noting, if we go back here, that these p-divisible groups over here, they really come from sort of abelian varieties. So abelian varieties. So in particular, a p-divisible group, the prototypical example is that you take an abelian variety and then you take the collection of its p-infinity torsion over here. And the moduli space of abelian varieties, that can be connected to this discrete automorphic spectrum appearing up here. So in particular, you can consider, what's known as a Chamorro variety. So this is some pair of some connective reductive group G and some co-character X. So, and X is going to be some conjugacy class of co-characters from some, what's known as the Deligne torus to this G of R. So this captures some information about the Hodge structures of abelian varieties. And if you act on this via G of R, then this is endowed with the structure of a real manifold or even a complex manifold. And so then we build this space, X times GAF. So here this denotes the finite adels, and then we quotient out by G of Q. And then we quotient out by some level K, where so K is going to be some compact open inside this finite adelic points. But this thing over here, well, this X, if you base change this to C, then that determines for you some kind of dominant co-character of this group, which is known as the Hodge co-character. So it's roughly encoding information about the Hodge-de Rham filtration on abelian varieties. And so this will be defined over C, but you can look at the stabilizer of the Galois group acting on that, and that will determine for you some number field E, which will be the reflex field. And then this thing over here, it's going to descend to some smooth quasi-projective variety defined over this number field. So there's some JK over here. And this thing even has some kind of compactification, which is projective. And the point is that, well, G of A acts on this set, and so G of AF will act on this set and will act also on these two spaces over here. Right, so these spaces over here, there's some moduli space of abelian varieties, and they can be related to what was explained up there. So in particular, we now need to relate the discrete spectrum to precisely these spaces appearing here, and to do this, we'll take cohomology. So in particular, we can consider some cohomology of this space up here, which I'll call R gamma shriek star GX. And this will be given by taking the cohomology inside this minimal compactification of some kind of, well, what will be an intermediate extension of this QL bar together with some Tate twist. So I'm kind of mixing compactly supported and regular cohomology, and the reason is I really want to just see sort of the discrete part of this spectrum over here. So you need to kill some kind of boundary terms having to do with the fact that this space over here is non-compact. So that gives rise to Eisenstein's theories and so on. Right, okay, cool. And then we can even, so if we want to see the full GA action, we can even take the co-limit over all these compacts. And, well, okay, this is going to have the action of some group G of A, so it's some complex with a G of AF action. And also, it has some action of the absolute Galois group of this kind of number field. So this is some number field attached to this co-character. And, well, you're not encoding any information about the Archimedean component, but if you fix some algebraic representation of G of base change to QL bar, then you can even encode that inside your cohomology. So there's maybe some C that we're fixing, and this encodes some information about the Archimedean component. So we have this crazy cohomology, but it turns out, and again, I'm just very heavily going to pass between complex coefficients and real coefficients, but this thing decomposes extremely nicely in terms of this kind of discrete automorphic spectrum. So there's some direct sum of this, and then you'll see kind of the finite part of this automorphic form, and that occurs with some multiplicity, m pi. And then there will be tensored via some complex, which will come from, so I'll call this a pi infinity c, which will come from the Archimedean component of this. Right. So,
Isn't that thing's included in this big thing, but you want to write modules after or something?
oh, sorry. Where do I want to?
QL bar join all that stuff. Can you put hyphen mod after it?
Oh, okay, yeah, sure. Yeah. Great, so now we're really seeing this space of discrete automorphic representations that we're trying to connect this thing to. And, well, this A pi infinity is in general complicated, but let me just remark that if you take pi of your local group to be, say, a supercuspidal representation, yeah, I mean, this is some GK cohomology if people care. But it's tensor by some complex, which I'll call A pi infinity, and then there's some thing having to do with this Archimedean component that you fixed over here, right?
Is it supposed to be a Galois?
I'm getting to that. But a priori, it's just some complex of QL bar vector spaces defined. It will be defined by a GK cohomology. So this is just kind of Matsushima's formula in the compact case. Right. Great. So now let me get to Jared's question, which is namely the Galois action on this. So if you start with some supercuspidal representation of your local group, well, okay, maybe I call this pi p, then you can find a globalization to a pi which lies inside this discrete spectrum, but it even lies inside what's known as the cuspidal part. So this is a cuspidal automorphic form, globalization to pi, such that this A pi infinity zeta for, let me just say, sufficiently nice zeta, so you kind of want this weight to be what's known as regular, so it's not fixed under the Weyl group. And if you do this, and again, I'm hiding an immense amount of work here, then you can arrange that this is actually going to be isomorphic, just as maybe a C or a QL bar vector space to this V mu occurring with some multiplicity n. Right? So in particular, now that tells us what Galois action that we should be looking for. So this is just as QL bar vector spaces. But this tells us actually that this A pi infinity zeta, okay, should actually be isomorphic to some phi pi. So this is a global Galois representation. So a global Galois representation attached to this cuspidal automorphic form, and then composed with this R mu, occurring with some prophylactic multiplicity here.
Maybe you want to remove the multiplicity in your expression of phi. Isn't it folded into the infinity?
I think there might be some discrete series L packet. This is just a prophylactic measure, so let me not make claims. The expert is sitting behind you, so. Yeah, right. Okay. So great. Now this global Galois representation, as you might imagine, because it's connected to this space of discrete automorphic forms, well, if you restrict it to this, so now you can fix maybe some QP bar isomorphic to C, and then you can fix, you can transport this Hodge co-character under this, and then that determines for you some local reflex field EP over QP. Well, then you can show that if you take this R mu composed with phi pi and you restrict it to this WEP, that is actually the local Langlands correspondence of the local representation composed with R mu. So let me emphasize here that this is not semi-simple in general. So this is really the local Langlands parameter incarnated as some continuous Weil group representation via these multiple different ways of thinking parameters that we've encountered in this talk. Right, so let me just say that there's an immense amount of work here. So, I mean, Sagwu is the local expert. There's work of Morel here, Yihang Zhu, Kissen Shinju, a lot of earlier work before that, but this is roughly the picture that you get. And so now, well, all we have to do is we have to connect this complex up here to what we were doing up here. And this is some moduli space of abelian varieties. And you can do this through a very nice theorem. So this theorem is basically where this work of Van Hoften, Kim, Zhang, and Patrick Daniels comes in. But you can show actually that there exists a sheaf, F shriek star, in this category of sheaves on Bun G, such that when you apply a Heck operator to it, and then you restrict, this is isomorphic as sort of a G of QP. So we just focus on the G of QP and then the local Weil group structure to this intersection cohomology complex that I wrote down. And let me just say something brief about the sheaf. The point is that the sheaf, it encodes what are known as Igusa varieties, but that's essentially going to capture the fiber of this map from abelian varieties to p-divisible groups. So this is kind of where the sheaf F shriek star really lives. So you need to capture information about the cohomology of the spaces you lost here. There are multiple people who know a lot about this here, so, but you can do this, and then once you have this, you can just do the same logic that we applied before, so you know that R mu composed with pi p is the same as R mu composed with phi rho p Fargues Scholze. So here, if you really do this carefully, you need to sort of pass to semi-simple quotients, so you really see this kind of semi-simplified parameter here. But again, it really just follows formally from this kind of relationship in just the same way as the usual compatibility followed from Harris-Taylor. And then for sufficiently nice minuscule mu, so in particular, the things that appear here, as kind of Jared alluded to already, this will imply actually just that the original thing is the semi-simplification of the Fargues Scholze parameter. So in particular, sometimes these minuscule representations, they lose in for too much information, and you can't do this claim. And so, for example, in the symplectic group case, that's basically the main obstruction. But in a lot of other cases, this kind of reasoning works, and you can show this kind of compatibility. Right. OK, so now how much time do I have?
Like 6 minutes.
Great, terrific. Any questions? I'm sorry, but like, you know, this, as you can kind of see, this topic, it connects a lot of different things, so I didn't really know what else to do. No, so the action of the Weil group comes solely from this Hecke operator, in much the same way that, well, the action of the Weil group via something like Mantovensk filtration comes solely from the Rappaport-Zing space, or the local Chamorro variety. So this sheaf, it has some away from P Hecke action, but it doesn't have an action of the Weil group. Yeah, and in this isomorphism, I forgot all the structure, I should say, aside from the local stuff I'm interested in. That's maybe some point to emphasize. Great. OK, so I'm going to now talk about a subtle but interesting point. Subtle but interesting point. So as I kind of mentioned up here, when you do this kind of globalization procedure, you really want to at least assume that your representation is supercuspidal for this globalization procedure to work well. So you really want pi b to be a supercuspidal representation. So want to assume And, well, you can do this. In particular, you know that Fargues-Scholze is compatible with parabolic induction, and so it's not too hard to reduce to the supercuspidal case by using induction on the levies. But actually, when you really do the details of this, it's even better to assume that pi b sits in a packet with only supercuspidal representations, with only supercuspidal representations. So pi b. So in particular, as we saw in Alexander's talk, that doesn't always happen. So this is equivalent to assuming that the parameter attached to it is supercuspidal. So in particular, it's semisimple, so there's no SL2, and it's discrete, so it does not factor through a levy. And basically, the reason for this is that all of this stuff up here goes through something that's known as the trace formula. And in the trace formula, you have to plug in a function that will detect this local representation. But you're not allowed to just plug in any function. You have to plug in what's known as a stable function. So you can't just plug in the function attached to pi b, but rather all of the representations in the packet. And so you want those all to have good analytic properties, and in turn, you want this assumption. But let me just remark is that you can actually reduce to this case. So one thing I really enjoyed when I was working on this is that there's this kind of interplay between local and global ideas, and this is some nice example of this to this case. So let me illustrate this maybe in just a quick example that I think, well, I don't know, I think this idea will come up at multiple points, but I just think it's good to do this one example. So in particular, I'm going to take G to be equal to GSP4. I'm going to take GB, or I'm going to take mu to be this Siegel co-character that appeared in Mingja's talk. So in particular, the dual group in this case is the same as G spin 5. But that's magically the same as GL4 in this case. And so, what? It's not GL4, thank you. Yeah, I proved this amazing result. Right, but in particular, if you take this co-character mu, so this is going to identify with the spin representation, and that's going to map towards this GL4 over here. But under this isomorphism, that is the same as actually the standard embedding. So this is the happy miracle we take advantage of for GSP4 that fails in general. So in general, the spin representation will lose some information. Great. And so then we take B to be kind of this basic element inside this BG mu over here. And right, so in this case, this GB is going to be some kind of inner form of GSP4. So it's GU2 of a quaternion division algebra. And let's consider some parameter that behaves as in the way I was expecting above. So you can take some parameter such that when you compose it with the standard representation, you get phi 0, and then chi tensored by some two-dimensional representation of SL2. So now you can compute by virtue of the fact that this is direct sum. So in particular, this is not supercuspidal. So there is some monodromy appearing here. Then, well, you can look at the centralizer group quotient out by the center, and then the fact that there's a direct sum here tells you that this is Z mod 2Z. And so you can look at the L packets in this case. So this is given by some pi supercuspidal. So there's one supercuspidal representation and one non-supercuspidal representation. And then there's a similar kind of behavior over here. And now I'm going to show you the great trick. So I'm going to consider this isotypic component in this case, so the same thing like the Lubin-Tate tower we were doing before. And I'm going to take the isotypic component of this non-supercuspidal representation. So this is some representation, so has some action of GSP4 of QP and the Weil group, but I'm just going to consider its class inside the Gerdendy group. And moreover, you can even maybe project to some nice analytic locus given by these supercuspidal representations. So you can project to the supercuspidal Bernstein components. Now, these two things are related by what are known as the endoscopic character identities. So there's some direct way of comparing representations of these two groups. So these were written down in Alexander's talk. And those endoscopic character identities, they can be seen in the cohomology of these spaces via some kind of Lefschetz fixed point argument. So this was carried out by Hansen, Kalitha, and Weinstein, building on some work of Mieta, who I think also did this GSP4 case, and that was in turn, I think, came from Foltings. But you can show, actually, and this is completely general, anytime you have these endoscopic character identities, that this will actually see two copies of this supercuspidal representation. So in particular, now you know that if you take the Fargues-Scholze parameter of this non-supercuspidal representation, it's the same as the Fargues-Scholze parameter of the supercuspidal representation. So this came up before. We already used this reasoning. It's very general. And that, in turn, tells you, so by induction, we already know, because this is a non-supercuspidal representation, so it's induced from some parabolic induction, that this is the semi-simplification of the usual correspondence. And we also know, because, well, I mean, the packets are the same, that this is the same over here, and in turn, we deduce to this. So in particular, the point is that using this Hansen, Kalitha, and Weinstein thing, you can always show that Fargues-Scholze is constant on L packets. So there's some beautiful elucidation of these ideas through Chenji Fu, and then David expanded on this even more. So we can talk about this later if you want, but yeah, I mean, that essentially allows you to reduce the case where all the members in the packet are supercuspidal, and then that feeds very nicely into this global trace formula input. Yeah, okay. Thank you.